Good morning, everyone. First, I want to thank the organizers of this meeting for giving me an opportunity to present some of my work. My name is Tchetgen. I'm a trained biostatistician, but I have joint appointments in epidemiology and biostatistics. And this talk is going to be very different from the previous ones. I'm more of a technical kind of person. What I really wanted to do today is convey a message about some of the work that I do. I worry a lot about causal inference. Causal inference becomes important when you can't run experiments and you try to draw causal conclusions from just observational studies, where you have no control over how the data arises. And what I want to do my presentation on causal inference is essentially going to be at the intersection with infectious diseases. As the title of my talk suggests, what I would like you to come out of this talk with is that the field of infectious diseases can learn from recent theories of causality and vice versa. This is joint work with a colleague of mine, Tyler van der Wiel. This is a quick plan of my presentation. I'll start with introduction and useful definitions. And then in those definitions, I'll try to highlight some of the assumptions that are usually made when we try to draw causal conclusions. Causal conclusions, we try to draw them in many fields, in sociology, in epidemiology, in economics, in many social sciences. The basic message is that some of those assumptions are violated once we start talking about infectious diseases. The main violation is one which I'll call interference. It's known as interference. And then to try to get an understanding of how interference manifests itself, we'll discuss a very simple case in a household of two people. And there we'll see that interference actually leads to new contrasts, new effects that we might not consider in non-infectious disease settings. And there are particularly there are some kinds of effects that Mark mentioned earlier, this type of effect known as herd immunity. And there was a question that was raised as to how is it that herd immunity in some cases appear to be much larger than direct effects. And we'll try to actually understand the different versions of herd immunities. What are the different mechanisms by which herd immunity could actually help in delivering a very strong effect, for instance, in vaccine settings. So why don't we get started? So as an introduction to causal inference, it's important to recognize that there are generally two notions of causation. The first notion is where we worry about the cause of an effect. That is, we first observe an event, and subsequently we wish to identify the cause that led to that event. And then there's a very different notion of causation, which is the reverse. In this particular setting, we wish to assess the effect of a particular cause. That is, we wish to assess the effect of a very well-defined exposure or intervention. And an example for that is that smoking caused lung cancer. Does a particular form of HIV drug prevent the advent of AIDS among HIV-infected patients? An example of the first type of notions of causality is in fact one that's very familiar. That is in the 80s when there were unusually high numbers of patients showing up with a combination of syndromes, including a form of skin cancer as well as pneumonia. The primary scientific objective at the time was to identify the cause of the outbreak. Eventually it was found to be HIV. So this talk is related to mainly the second notion. It's most common to the health sciences as well as the social sciences. That is, we have a very clear idea of an intervention that we wish to implement, and we would like to understand whether that intervention would have the desired causal effects. Okay? This notion of causation should be familiar because it falls, in fact, under the usual experimental paradigm that we might use in other kind of more biological sciences or chemical sciences in a lab. And this connection is made explicit in the context of randomized experiment. Randomized experiment is the way the FDA wishes that drug companies actually assess the efficacy of their drugs. Is to actually randomize patients to take the drug or not, as a way of proving causation, that the drug actually does work. But these notions of causation are still useful paradigms when experiments cannot be performed. And in such settings, experiments cannot be performed, for instance, to assess the effect of smoking on lung cancer for obvious ethical reasons. So that you might ask, why do we need a formal theory of causation? Well, formal theory of causation might help make explicit what we mean by causal effect. In the English language, we use it all the time. That is, what exactly do we mean mathematically? What is the quantity that we seek to understand? It might also lead to some explanation about some popular sayings. For instance, you might have heard association is not causation. So what does that mean? And why is it that a lot of people believe statistical methods can never be used to establish causation? That's usually tied with this saying. But it also gives conditions under which association is causation, as in the case of randomization. I just said randomization is a gold standard for establishing causation of an intervention. And therefore, standard statistical methods may be used. Generally, a formal theory of causation would make explicit assumptions needed for the identification of causal effects and would allow for the derivation of new statistical methods when standard methods fail. Okay, so to make these abstract notions more concrete, let's consider a very specific example. Okay, you're sitting there and you have a headache. And suppose you're now contemplating taking an aspirin for your headache. And I'm going to use Y to denote the outcome an hour later of whether or not you remain with your headache. Okay, so Y equals 1 is if after an hour your headache remains, and Y equals 0 denotes if after an hour your headache is gone. As a thought experiment, you may think of two potential outcome variables, either of which may be observed depending on whether or not you take the aspirin. And so these are attributes. We're going to imagine that these attributes are in existence prior to our decision to take an aspirin. There's going to be an outcome for each of us. What would happen if, in fact, to my headache after not taking aspirin, and what would happen to my headache after taking aspirin? Even prior to taking the aspirin, the model would say those attributes are part of our being. Okay? And so move from this individual-based model to a population model. And for that, it's useful to imagine that the population we care about is this population of 8 people. And I call this an oracles table because you imagine that this is something that would exist prior to any situation where you would have actually decided to take an aspirin or not to take an aspirin. And so each of those people would have a corresponding potential outcome. And the potential here, again, indicates that these are prior to what actually happened. This is what might happen to you under either of these states, whether you take the aspirin or you don't take the aspirin. And so you get different situations. For instance, the first person would remain with a headache. Would no longer have a headache, irrespective of whether or not they take the aspirin. So 0 here indicates you don't have a headache. Cool. And person 2 would have had a headache had they not taken an aspirin, and the headache would have been the aspirin would have been protective against the headache after an hour, and so on and so forth. You can interpret the outcome for each person as the outcome that you would observe if possibly contrary to fact you had followed a particular treatment, taking the aspirin for 1 and not taking the aspirin for 0. And little a here denotes your state for your aspirin state, if you will. And now we have a way of codifying what we mean by a causal effect, because if you look at the contrast, comparing your outcome without an aspirin to your outcome with an aspirin, well, the English sentence, aspirin has no causal effect on my headache outcome, is equivalent now to the mathematical statement about my potential outcomes. That is, y0 should be equal to y1. And so, for instance, for that first person, we clearly see that happening. y0 is equal to y1. And the contrast, y1 minus y0 is exactly 0. For some people, you could see that aspirin seems to help, in particular those who have a negative value. Means, if you recall, y equals 0 means you no longer have a headache after an hour. And for some people, aspirin appears to be harmful. Okay. And so this is one way of thinking about what's the underlying meaning of causal inference prior to actually observing data. Okay, these are latent value, latent state that we all walk around with. And faced with a certain situation and a certain decision, some of these outcomes might reveal themselves. In particular, now imagine that a person decision to take an aspirin or not is recorded in this variable a, which I denote as capital A to be distinct, which is distinct from little a, which was the effects value. Capital A is different for different people. This person did not take an aspirin. This person happened to take an aspirin, so on and so forth. And what we end up observing for that person is a coarsening of their potential outcome. In particular, if they decided not to take an aspirin, well, their potential outcome, had they not taken an aspirin, would be suddenly revealed. And so these two columns refer to the observed data, the data that we end up observing. It's clear that if we observe a given potential outcome for this person, for instance, who ended up taking an aspirin, we observe their potential outcome had they taken an aspirin, because that's indeed what they did. The other outcome becomes a counterfactual. We never get to see it. Okay. And so this is a very extreme form of a missing data problem. And this tells us that in reality, because our observed values are going to be a coarsening of the underlying potential outcomes, we never hope to actually be able to estimate. There is no hope to identify individual causal effects. That's completely, an impossibility. But however, one can actually hope to identify population average causal effects. That is, if you were to average over these 8 people, what would have happened under each state? You would see that in this particular population, the effect was actually a quarter. And I'm going to use E to denote averages over population here on forward. Okay. And an easy way to achieve this identification is to actually randomly assign people. This is the idea of randomization. You randomly assign people to take aspirin by a coin flip. Then one gets from the observed data that was here. This is actually what I did. And you can check. You can check that I randomized because you had 8 people, and exactly 4 people took aspirin and 4 didn't. And so they had a probability of half to take aspirin. But I did this at random. And it turned out, just using the observed data and not having access to both potential outcome, if you were to compute the average of the outcome among those who ended up taking aspirin, this person, that person, that person, that person, and you were to contrast that to the average outcome among those who happened not to take aspirin, you recover exactly the population average causal effect you were seeking for. And so under this access to randomization, we can in fact recover average causal effects. Okay. And so now you're all experts in causal inference. Okay. All right. So that was a way of introduction, because the previous example made the implicit assumption that a person's outcome can only depend on his or her exposure, and not on the exposure of another individual. This assumption is typically made in the health sciences, but also in the social sciences. We're going to say that interference is present when the outcome of one individual depends on the exposure of another. Okay? In many settings, interference is almost certainly present. That's going to be true in infectious diseases, obviously, and vaccines. In tutoring and education, it turns out that these manifest themselves. These effects are also manifested. And also in the judicial panels. Interference is very different from other kinds of dependence. There are other kinds of dependence that may happen. You may have clustering because the outcomes that you observe are correlated. Or there's this idea of contagion, which is very popular in the study of social networks, and we'll come back to this. That's also very different from interference, but they're closely connected. Until recently, it was thought that inference with interference was intractable. And I summarize, I'm not going to go through this in detail, but I give you a short history of the concept of interference. How can we relax the assumptions typically made in causal inference. Okay. And going through this history, you will see that ideas appears in statistics, in infectious disease context, in the social sciences, as well as in econometrics. All right, so let's try to see how we can make progress once we relax the assumption of no interference. And to do so, I wish to consider that we have n clusters of size 2, a very simple setting. The size 2 could be a household consisting of a wife and a husband. Suppose further individuals in one household do not interact with those in another household. Okay, and this is going to be generally true if, in fact, your study consists of a small proportion of the entire city, say, chosen at random. And what I want to do now is I'm going to introduce some more notation. We're going to denote Aij, whether individual J in cluster I receives a vaccine. And what's going to be important here is really, I want you to keep track of J. For the individual, it's going to be 1 or 2. Forget about I, because I'm only going to focus on one cluster at a time. And similarly, we could define Yij to be the indicator of whether the person is infected. And now we need notions of potential outcomes that allow for interference. And the way we achieve this is essentially, we'll use the same notation that we used before to denote the potential outcome of an individual under a given exposure or a given condition. But now we have to make explicit that that person's outcome, J's outcome, not only depends on his or her exposure, but also on his or her partner's exposure. Okay? And so this denotes whether individual J in cluster I would have been infected had individual 1 received treatment. That's the first treatment A1, where A1 could take the value 0, 1. Individual 2 received treatment A2. The setting consists, considering 2 people simplifies things tremendously. And yet all the key ideas are preserved. So it's useful to consider interference in the simple setting. The potential outcome for individual 1, Yi1, A1, A2, depends both on the treatment received by individual 1 and by individual 2, and likewise for persons 2's outcome. The assumption of no interference is that each individual potential outcome depends only on the treatment received by that individual. And now you see that the usual assumptions made in causal inference is a special case of this extension, where we just assume that the person's 2's exposure does not affect your potential outcome. The other person's exposure doesn't affect your potential outcome. Okay, I'm going to skip that. Once we've made these potential outcomes allowing for interference, we can now define the following effects. Recall that earlier we defined contrast, individual level causal effects. Similarly, we can define such contrast in the presence of interference. And I want to start with the total effect. And it turns out that now you get different types of effect. These potential outcomes allow you to encode different types of effects. So if we start with the total effect, imagine what would be the potential outcome of person 1 had neither been exposed to a vaccine, versus that person's potential outcome had both individuals being exposed. And we're going to refer to that as the total effect of vaccine. And it's going to turn out that total effect can be decomposed. Okay? They're going to be individual or direct effects. That is, you simply take the contrast of the potential outcome for person 1 when person 1 is treated versus not treated with the vaccine, holding person 2's status fixed in that comparison. And you can see, similarly define a spillover or indirect effect. And intuitively, that should be what is the influence of person 2's exposure on person 1's outcome. And that's what this is encoding, irrespective of what person 1 receives. Overall effects could similarly be defined. We could likewise define these effects for individual 2 or we could average over the individuals, and these are known as group averages, or we could average over clusters. These are known as population averages. And this is the key point, is that the total effect decomposes into an individual and a spillover effect. That's the total effect, can be broken up into two effects. So there are two effects that are operating. And this notion of herd immunity might be conceptualized as an indirect effect. Now we have it encoded mathematically. Suppose now that we were to randomize each individual within the cluster, flip a coin twice, then it turns out these various contrasts are fully identified. The same way we discussed randomized trial allow you to identify causal effects in a standard setting with no interference. And this can be done just by taking averages and given samples. I'm not going to go into detail, but it can be done, just randomization buys you that. And so these various types of effects could in fact be identified under this specific design where you randomize each individual within a cluster. These effects were first considered informally back in the early 90s. These effects were further formalized also in settings without an arbitrary number of individuals per cluster. As we discussed, identification and inference is straightforward with clusters of size 2 if treatment is randomized for each individual. Definitions become a little more complicated with larger clusters, and we'll briefly cover that later. So what I want to do now is I want to zoom into these indirect effects, okay, into herd immunity, and talk about various kinds of indirect effects. So an important type of indirect effect is so-called an infectiousness effect, which may arise when, if we in fact found a non-zero spillover effect. So we have evidence from our randomized trial that there is some herd immunity. And we'd like to understand how it manifests itself. That is, vaccinating individual 1 has an effect on individual 2, even when individual 2 is not vaccinated. That's what we mean. We might imagine different explanation for such a protective effect. For instance, it might turn out that vaccinating individual 1 may prevent individual 1 from being infected and therefore prevent individual 2 from being infected. Or it might turn out that even if individual 1 is vaccinated and subsequently infected, the vaccine may still make that person less infectious. The second effect is sometimes referred to as an infectiousness effect. So now that we have this language of potential outcomes, can we actually rigorously formalize this idea and think about identifying this particular type of indirect effect from experiments? How might we more rigorously conceive of such an infectiousness effect? Well, consider the very strange quantity. So it's still an average. The bar just means that I'm going to restrict my inferences on a subpopulation of interest. And the subpopulation is characterized by these people. So these people are people who are doomed. They're going to be infected irrespective of whether they receive the vaccine. So person 1 in each cluster in this population is doomed. And I want to understand what is the effect of the vaccine on person 2 in that subpopulation. That goes straight to the idea of infectiousness. Because person 1 is going to be affected no matter what you do, whether or not you infect them, you vaccinate person 1. And we want to understand person 2 is not vaccinated. We want to understand the effect of the vaccine on person 2 infection status. These types of strata are known as principal stratum because they're defined in terms of potential outcomes. They're very strange because we don't observe the potential outcome. This is a wishful thinking, right? We never observe both states on a given individual. And so we can never hope to identify this. But it turns out under very simple condition, you can get an upper bound. You can get a lower bound on how small this effect might be, or how large this effect might be. In other words, you can compute from your observed data a number such that you know that the infectiousness effect is no smaller than that number. This is known as conservative inference. The assumptions that you need are known as a monotonicity assumption, which states that the vaccine cannot be harmful. It's a reasonable assumption. And the second assumption states that the clusters in which individual 1 is vaccinated and infected are generally worse off than the cluster where individual 1 is vaccinated and not infected. That's also a reasonable assumption. Well, under those two assumptions, it turns out that this idea of bounding the infectiousness effect is very simple. You can actually do that from a randomized study. And you could do it on different scales. I'm not going to go into detail about that. So let's consider an example. This was a study that analyzed results from a group randomized trial, 2 vaccines, one for pneumococcal conjugate vaccine, which was compared to meningococcal conjugate vaccine against serotype C, serogroup C, among Southwestern American Indian communities. The vaccine was administered to children in some households, but not others. And the outcomes were also collected on all adults. The vaccine for the children had a protective effect on adults in the household. And I just want to think of the odds ratio as a measure of relative risk. And less than 1 means, in fact, the vaccine is protective. So this was very smaller than 1. It had an effect on the adults. And the idea was we further wanted to understand the infectiousness, how large the infectiousness effect would be in this population for the adults. So they further considered outcomes for adults comparing households in which the vaccinated child was colonized versus households in which unvaccinated children were colonized. And this is the idea of comparing empirically, looking at the data, and obtaining this would provide a low bound for the infectiousness effect. And in fact, there is statistical evidence that that infectiousness effect was in fact operating in this study. This naive estimator is conservative for the infectiousness effect under the both assumptions that we gave, thereby providing evidence of a true indirect effect and further characterizing the nature of that indirect effect. The methodology that I've described here is applicable generally to households and not restricted to the vaccine study. You could apply it to other settings as well. I think I'm going to skip ahead a little bit because I have 5 minutes and I want to get to I have 3 minutes. I had 5 minutes. I want to briefly comment on social networks, and I think there are 2 speakers later this afternoon who are going to give us much more detail about social networks. But it turns out that these notions of causal inference can be adapted to studies of social networks. Okay? We've seen throughout that individuals in one cluster do not influence individuals in another. As we relax this assumption, we move towards social network analysis. In a social network analysis, one person's state may influence that of a friend. There are a lot of such analyses that have been published, but the most popular ones, the most famous ones, are done by these 2 collaborators, Christakis and Fowler, and that has suggested that such social influence plays a role in the spread of things such as obesity. If your friend is obese, apparently it makes you obese. Makes you more likely to be obese. Smoking, happiness, loneliness, so on and so forth. So one question that we approached when we looked at this literature is whether this is what we conceive as interference. And if so, whether we could characterize these as spillover effects, indirect effects. To understand the difference, the distinction, is in fact useful to consider this following diagram, and this is for one person versus another person. These are covariates. They're just environmental behavioral variables for each person. This is the outcome measured at 2 different times, time t and time t plus 1 for person I, time t plus 1 for person k. And the question about contagion is asking about whether this arrow is here, this arrow, whether person's k's outcome influences person's I outcome at time t plus 1. And the methodological concerns here are actually very different. They're actually more severe because there's this idea of homophily. It's a very strong form of confounding. That is that people are friends, people belong to the same social network, mainly because there are underlying reasons that may not be observed, right? That there are attractions within people, there are similarity that make them very similar. And so there's a concern that that similarity may actually explain the influence. That what you're observing is not so much causal or contagion, but rather a reflection of this particular form of homophily, of confounding. So similar methodology to what we've considered in this course. This is a course. You're going to get an exam, a take-home exam, can sometimes be employed. Sensitivity analysis can be used, however, to assess the extent to which estimates of contagion are robust to homophily, to these forms of latent confounding. And it turns out that when you do that, the presence of my collaborator Tyler wrote a paper on this, and it turns out that once you try to see the extent to which your inferences, social network studies that have looked at these various forms of contagion can be explained away due to confounding, that they're really biased and not measuring what we might think as contagion. It turns out that the contagion effect for smoking and obesity seems fairly robust to fairly substantial presence of confounding, of homophily. But that for happiness and loneliness are considerably less robust. Okay. Allowing for a little bit of bias, they vanish. But the truth is, these effects are really associations adjusted for variables responsible for environmental confounding and homophily. And it's hard to conceptualize them as causal effect. Okay? So what we've been trying to do is essentially use this framework of potential outcome, essentially to translate what you might imagine to be a contagion effect, as we've done today, what you might imagine might be a causal effect on a social network. And I think I'm going to stop here. Thank you.
Hello, my name is Kevin, and I was actually trying to look at your cause and effect, equation that you came out with, and talking about, how the outcomes of, the first person who was involved, or one representing the one who's actually, taking the aspirin and the one who's not taking the aspirin. You wrote this equation, y equals a, the capital A, which was actually the parameter, times y1 plus 1 minus a times y0 actually at the beginning. And my question, exactly that one. So I was wondering, how did you come to that one? Does it refer to, is there any general equation that you actually, we have to use, or how do we come about to create such kind of equation, pretty much?
No, thank you. I appreciate your question, because I inadvertently skipped this. So I'm glad you brought me back to it. So what this is actually saying is, essentially, you imagine these potential outcomes at latent states that we all want to know. And when we're faced with the decision to take aspirin or not once we have a headache, and that decision will reveal why is what ends up happening to you. Is what, if you might come back an hour later and look at this group of people who have a headache, had a headache because of my talk, that's taking aspirin, why would tell you, for those people who happen to take an aspirin, well, the outcome would be the potential outcome they would have experienced had they taken an aspirin. Because indeed, they took an aspirin. And that's because A would be 1. You would see Y would be equal to Y1. A equals 1, this term goes away. And vice versa. For those who didn't take aspirin, you would observe Y0. And so this equation is simply encoding what you imagine would be the most natural thing, which is that once you observe an outcome, there's an assumption here that the outcome that you observe is in fact the potential outcome revealed by taking an aspirin or not taking an aspirin. Yes, Mark?
Can you comment just for a minute? You mentioned vaccination as one kind of intervention that has interference effects. Do you want to describe at all other interventions like circumcision or other drug treatment, other things, and how they would fit in this framework, just as example? I mean, briefly, just as examples.
Sure. Or you could comment on it. Yeah, no. So I focus on vaccination because that's the most straightforward, sort of intuitive notion of interference. But there are many other settings where we might imagine that interference might be operating. For instance, as Mark mentioned, circumcision might be one such setting, where you imagine that a woman having intercourse with a man who happens to be HIV infected. Well, the woman's risk of HIV infection not only depends on her behavioral factors, but also happens to now we know that circumcision actually helps prevent HIV, reduce the risk of HIV infection. And so that translates essentially into an interference effect, that the partner's circumcision status affects the woman's HIV status. So that's one that comes to mind directly because you mentioned it, but there are many others.
It's lunchtime, so we'll be back here at 1:40, but definitely take advantage of talking to all the faculty at lunch.